Hi, my name is Mitch Van Ochten. I'm a Senior Applications Engineer with ROHM Semiconductor in Novi, Michigan. This presentation will cover ROHM's DC to DC converters for automotive electronics applications. These parts meet AEC-Q100 automotive requirements in either grade 0, -40C to +150C, grade 1, -40C to +125C, or grade 2, -40C to +105 degrees C. The AEC-Q testing requirements are more difficult to pass than testing typically done for consumer ICs, and in general, the result is higher reliability at slightly extra cost. ROHM offers several categories of regulators for automotive applications. The largest category is linear low dropout regulators, and after that the switching regulator category, which includes buck, boost, flyback, and power management ICs, PMICs. Year by year, the number of regulators needed per vehicle has been increasing. This slide shows many of the automotive applications requiring some type of regulator. The recent increase in demand for AEC-Q products revealed to many customers which of their suppliers could be relied on for delivery during tough times. Many opportunities opened up for ROHM to fill the vacuum created when larger companies could not deliver. ROHM believes in vertically integrated production as much as practical. Our Yokohama Technical Center, YTC, has an anechoic EMC lab and can perform both conducted and radiated emissions testing. Our Novi lab can assist with conducted emission tests per CISPR 25. Japan can also assist with thermal design using FlowTherm software for thermal simulations and to predict how hot your part will get based on the available copper area, number of layers, thickness of the copper, and airflow. They also have a Mentor Graphics T3 stir system, which can be used for characterizing complete systems or thermal management devices such as heat sinks and heat pipes and the resistance of thermal interfaces. ROHM has improved their DC to DC converters in several ways. One of these is called Nano Pulse Control, which allows a very small minimum on time. This makes it possible to do conversions from 60 volts down to 2.5 volts in a single regulator instead of two stages. You can still use fixed frequency mode, which avoids skipping cycles and gives a well-defined EMC footprint. We also offer what we call nanocap technology, which reduces transient response variations of the output, improves the dynamic response. Finally, we are reducing quiescent current, which reduces battery drain when the part is not switching. This slide shows details of the benefits of Nano Pulse Control. Take, for example, our BD9V100 MUF. This part can accept a DC input up to 60 volts and deliver an output of 3.3 volts. On account of the small on time, when operating at a 2.1 MHz fixed frequency, the conversion can be done in a single stage. Also, the 2.1 MHz is beyond the top of the AM broadcast band, making it easier to meet automotive EMC requirements. In addition to permitting large differences between V-in and V-out, another advantage of Nano Pulse Control is improved line regulation response. Here we have oscilloscope waveforms for our BD9P255 MUF family compared against two competitors. In the upper row, V-out equals 5 volts at 1.5 amps. V-in switches between 16 volts to 8 volts and back to 16 volts. You can see the effect on the output for the ROHM part is less disturbance than two of our competitors. In the second test, the V-in switches from 16 volts to 4 volts and back to 16 volts. This causes the regulator to drop out of regulation and then to recover. The size of the recovery overshoot is far lower with the ROHM part. Such good dynamic performance is hard to determine by simply comparing the datasheets. We call parts with nominal V-in greater than 5.5 volts primary switching regulators. This chart shows synchronous primary parts which use N-channel MOSFETs for both the upper switching device and the lower synchronous rectifier. In order to get the required gate drive voltage for the upper NMOS switching device, all these parts use a capacitor charge pump. The next page will show other parts incorporating a PMOS device for the upper switching device. This eliminates the need for the charge pump capacitor and in some cases permits 100% on time, allowing extremely small difference between input and output voltage. Based on the desired Vout and desired current, the chart allows you to easily find the best part. Some of the parts shown here are not available yet. This chart shows primary synchronous parts incorporating a PMOS device for the upper switching device and an NMOS device for the lower synchronous rectifier. The upper P-channel MOSFET eliminates the need for the charge pump capacitor and in some cases permits 100% on time, allowing extremely small difference between the input voltage and output voltages. Here's an example of primary DC to DC converters in the 1 to 2 ampere range. These parts accept anywhere from 4 volts to 40 volts input and operate at 2.2 megahertz, and you may choose between forced PWM, which is fixed frequency mode, or SLLM, simple light load mode, which skips cycles at light load for higher efficiency. Output current limit is pin selectable between two values. You may select spread spectrum if desired. Shutdown current is a minuscule 2.1 microamps typical. These parts are available in two packages, HTSSOP B20 or the VQ-FN24F V4040 package with 20 pins. These parts are almost identical to the BD9P1X5 and BD9P2X5 family, but not pin compatible. Output current is pin selectable between two values. You may select spread spectrum if desired, and the shutdown current is a minuscule 2.1 microamps typical. They are available in the VQ-FN24F V4040 package with 24 pins. This 3-amp primary synchronous DC to DC offers a choice of operating frequency of either 2.2 MHz or 440 kHz, pin selectable. Input range is 4 volts to 40 volts, and an output current up to 3 amps is available. You may select spread spectrum function if desired. The BD9P233 MUF is a primary synchronous DC to DC which can operate from 200 kHz to 2.4 MHz. Since it uses a P-channel MOSFET for the upper switch, it does not require a charge pump to develop gate drive and can be operated at duty cycles up to 100%. It has a fixed output voltage of 3.3 volts and can deliver output current up to 2 amps. The BD8P250 has an input voltage range from 5 volts to 36 volts and can deliver an output of 5 volts at 2 amps. It's a primary DC to DC which operates at a fixed 2.2 MHz frequency. It offers a low quiescent current of 8 microamps typical. The BD906XX family of primary DC to DC converters is unique. They are non-synchronous parts, meaning you must add the catch diode from the switching pin to ground to allow the coil current to recirculate when the power switch turns off. For this family, the power switch is a P-channel MOSFET, and the parts support a duty cycle including 100% on time. They can operate at switching frequencies from 50 kHz to 600 kHz and are available in 3 different current ratings. The BD9901 is a synchronous primary DC to DC which can accept 4 volts to 42 volts input and can deliver 3.3 volts or 5 volts at up to 2 amps load. It can operate from 200 kHz to 500 kHz and can operate in either forced PWM mode or in light load mode where it may skip cycles to improve efficiency at light load. It includes a P-channel and an N-channel output MOSFET and can operate at up to 100% duty cycle. This chart is a collection of primary devices not shown elsewhere. It includes some non-synchronous devices, controllers requiring external MOSFETs, and some buck-boost devices. This is a 2-chip solution for a buck-boost application which can accept a nominal 7.5 to 36 volts input, and in boost mode it can deliver a fixed 5 volts output even when the input drops as low as 2.7 volts. It operates at a fixed 2.2 MHz. The BD9V100 is a synchronous primary DC to DC which can accept input voltages ranging from 16 volts to 60 volts. Output voltage is adjustable from 0.8 volts to 5.5 volts at an output current of 1 amp. Switching frequency is adjustable from 1.9 MHz to 2.3 MHz. This part includes a P-good output function, which is sometimes useful. The BD9036EF is a buck-boost controller which can operate from 100 kHz to 600 kHz, and it has an internal phase lock loop to allow synchronization with an external clock. It is intended to drive an external N-channel and P-channel MOSFET and 2 catch diodes. Input voltage is typically from 4.5 volts to 36 volts, and the intended output voltage is from 0.8 volts to 24 volts. The amount of output current is dependent on the external components selected, but typically around 3 amps can be expected. The BD9015 is a 2-channel synchronous primary buck converter designed for use with 4 external N-channel MOSFETs. The input can accept 5 volts to 30 volts, and each of the 2 outputs can be adjusted anywhere from 0.8 volts to 10 volts. The basic operating frequency is 250 kHz to 550 kHz, and the part has an internal phase lock loop to allow synchronization from an external clock. Here is the roadmap for our primary DC to DC regulators for the next 2 years. The BD9P608 MFF and the BD9P305 EFV are currently on our website and should be available soon. Other parts shown as in planning or in development may not materialize. Here's the roadmap for our primary buck-boost and higher voltage DC to DC regulators for the next 2 years. Only the BD9V100 and BD9036 shown at the left are active at this time. Previously, we discussed the Nano Pulse Control and how it is a benefit in applications with a large difference between input and output voltages. We would also like to mention our QuiCur technology, which can be found in certain low dropout linear regulators as well as some DC to DC buck regulators, and enables improved dynamic load response and in some cases a reduction in the size of the output capacitor required. We refer to automotive parts with V in equal 5.5 volts as secondary regulators. This chart gives a nice overview of our single-channel buck part availability versus output current. All of these parts operate at 2.2 megahertz, which is just above the AM broadcast band in a region where the automotive EMC specs are relaxed. The BD9S200, 300, and 400 is a family of 2 amp, 3 amp, and 4 amp buck converters in the small 3x3 millimeter package. They can operate in selectable light load mode or forced PWM mode with a mode select pin. They also include a power good output pin. The BD9S000 or 100 is a pair of 0.6 amp or 1 amp buck converters in an even smaller 2x2 millimeter package. They have built-in phase compensation and include a power good output pin. The BD9S201 is a 2 amp buck, also in the small 2x2 millimeter package, and it has built-in phase compensation and includes a power good output pin. It also features an output discharge function which connects an 1100 ohm resistance from the switch pin to ground when the part is disabled or when V-in becomes too low. The BD9S201 is also a 2 amp buck in the small 2x2 millimeter package, and it has built-in phase compensation and includes a power good output pin. However, it does not include the output discharge function. Here's the roadmap for our secondary switching regulators. The BD9S402 incorporates both Nano Pulse Control and our QuiCur technology, enabling less output capacitance. The other parts shown here are not available yet. This concludes our presentation of DC to DC converters. Many parts have Excel spreadsheets available to help with component selection. Also, upon registration, you can use the ROHM online solution simulator called PartQuest to try your design before building. And encrypted SPICE models are immediately available. LT SPICE models are generally available upon request. Evaluation kits are available for nearly every device we discussed today. Thank you for your attendance.